Okay, let's go for it. The subject today, well, the title of our introduction, Water Level Critical, Anticipating Changes to Our Most Important Resource. We have today with us two fairly extraordinary experts in this field from two rather different organizations, of course. The University of Cambridge, the head of the Polar Ocean Physics Group there, Peter Wadhams. You're a mathematician and a physicist, Peter, I guess, and you are going to be telling us, I guess, from that theoretical approach, what we are seeing in the trends and in the shifts, the very extraordinary shifts that are taking place in global precipitation, and how water trends are going to affect scarcity, of course, as well as abundance, are going to affect us around the world. Dalia Kirschbau of NASA, she is the Chief Hydrological Sciences, she's Chief of Hydrological Sciences, I beg your pardon, there. Dalia, disasters is one of these big areas you focus on. Describe to us, first of all, where you come from primarily with this subject.
Absolutely. Well, it's a pleasure to be with you. Thank you so much for inviting me to be part of this excellent panel. So I'm coming to you from Maryland in the United States. I work at Goddard Space Flight Center. And so in addition to being chief of the Hydrological Sciences Lab, which focuses on how we can examine the role of water and how it moves both with satellite observations and models, my research actually focuses on natural disasters and how we can harness the power of satellite information and models to better understand disasters in a near real-time state, as well as over a long period. So thank you so much. I'm excited for the conversation.
Peter, tell us about your work, specifically where you're focusing right now.
Well, at the moment, I'm looking at the Greenland ice sheet and why it is melting as fast as it is, and whether it's going to be melting faster in the future. Most of the time of my career has been spent looking at sea ice and its role in the ocean. But now at the moment, I think the greater threat is from the melt of ice on land and what that will do to sea levels, global sea levels.
And of course, Greenland is the largest, the largest block of fresh water anywhere, right? Of a single unitary kind that is in the ice, the form of ice, and can and is threatening, as you say, sea level rise perhaps more than any other single glacial block. Well,
it's the second largest. Antarctica is in the lead, but in terms of the melt rate, it's Greenland which is contributing most at the moment.
And how have you studied? I mean, how does that work? What is the nature of the study that you are most directly involved in now?
Well, first of all, the large-scale study really involves use of satellites that give the elevation of the ice sheet. But in my personal work, which is walking around on tops of ice sheets, it consists of looking at exactly what's happening to the Greenland ice sheet in terms of the content of the material that's on the top of the ice sheet, which is becoming blacker and blacker because as the ice melts, runs away quickly, the dirt is left behind, and the dirt is now enhanced by the addition of a lot of soot from the global brush fires that have been going on, and that makes the ice surface darker, and that means that it melts more quickly. So I'm trying to work out how much faster the ice is melting because of the additional dirt and soot that's being deposited on it.
Dalia, does NASA map this stuff as well? I mean, presumably it does. I'm afraid you're muted at the moment.
I am. As Peter mentioned, there's different satellites that are making both optical observations at the surface of all of these key ice sheets, both on land as well as sea ice in the water. And then there's elevation measurements such as ISAT-2 that are allowing us to look at the dimensions of the ice. But another part of that Peter highlighted is the transport of dust and different aerosols, so particulates in the air that can deposit, and this is Peter's area of expertise, on these key surfaces that, when you darken the surface, it actually changes what's called the albedo, and it can cause increased melting. And so by being able to have satellite observations of the surface of the ice optically, as well as look with a laser to look at the elevation, that's critical. But then we also have satellites that can look at aerosols and how those are transported from smoke, from dust, from other sources. And modeling those processes together is really fundamental to looking at kind of the bigger picture of ice sheet balance, which is not my area of expertise, but of the water cycle.
So the soot obviously makes it darker, and that therefore it absorbs more sunlight, which makes it warmer, which makes it melt faster, which causes, is that right, Peter? Sorry, I'm going to be very crude here for the non-scientists amongst us. That is essentially the process by which we are seeing this accelerated ice melt. Absolutely,
yes, and it's very, very highly visible now. Like last summer, I was standing on top of the ice sheet, and it was visibly melting. Waterfalls coming off it, water running down through the ice sheet towards the bedrock underneath, that particular day in August was the day on which there was more melt recorded than any other day ever. So it's a sort of the record day. I think 12 billion tons of water melted in a single day. So
it is an extraordinary experience. I mean, I've been to Western Greenland, and that moment when you stand in Disco Bay and you watch the iceberg, the icebergs forming as they crash into the ocean, it is an extraordinary thing to witness. But as you say, terrifying in the context in which we now understand it.
Well, yes, because you think about all that water, you know where it's going into the ocean, and you know that what that's doing is causing global sea level rise. And we know that there's nothing we can do about it. There are things we can do about other aspects of the climate. In fact, most of my work's been on sea ice, where you can devise ways to try to bring back sea ice if it's melting and so on. But you can't really do anything about global sea level rise. It's a sort of natural process in that it's happening because of global warming. We can't really change the rate at which it's happening, at least in terms of how people have thought about that, but you can't do it. So we have to, it's the one thing in the global climate that we have to sort of endure. We have to live with it, and we can't try to do anything to improve the situation.
Okay, well, I'm going to want to come back to that in a second. But Dalia, I mean, when I was preparing for this, I was searching, just recent news stories, and of course, the most dramatic rain event recently has been perhaps the flooding in eastern Australia, brought about, we understand, I think, from El Nino, isn't it? That's what's considered to be one of the triggering effects there. This is obviously a regular cycle, and it's completely natural, and it's a permanent thing. How are you seeing these trends of like excessive rainfall affecting the disaster kind of studies and mapping you've been doing?
Yeah, I mean, that's a great question. So, one of the many things that I do is trying to understand extremes in context, right? So being able to look at the satellite precipitation record, look at other elements, and determine how extreme these cases may be. Another example that happened recently was the devastating mudslides in Petropolis, where they had over 250, I believe, millimeters of rain within 3 hours in the steep hillsides outside of Rio de Janeiro. And so we were actually working with our colleagues in Rio to see how we could help both with optical mapping of where landslides are happening, as well as understanding the context of this extreme rainfall. And so, similar to the flooding in Australia, we know that the extremes are getting more extreme. Some are more attributable to climate change than others. But, as we see more extreme rainstorms that cause things like landslides, which is what I study, we're trying to get a better understanding of the impacts, right? So putting together all of the information we have from both satellites and models to understand how those extreme events may impact people. And so we have global models that are looking at this, for example, for landslides. We also have global flooding estimates where we can map, we can model these processes. And the goal is to really provide that information locally to the people who can take action and make decisions about how to save lives and property. And so at NASA, the goal is to really observe and to provide and support and enable information to be shared globally to better mitigate these hazards.
Can you have early warning systems for mudslides?
Pardon?
Can you have early warning systems for mudslides?
So early warning is tricky. So right now we have a global system that what we call is near real time, right? So the satellite data we can get within 4 hours. So within 4 hours, we can have a sense of where the extreme rainfall is that's causing landslides. We're also working on a global forecast, which my team will be deploying soon. But really what it comes down to is identifying the areas that that could be at increased risk of landslides so that local officials can make the warnings, right? So we don't want to be as a government agency and providing that type of information. It's very important to provide the tools and the information, both for what's happening now and maybe what's happening with the days into the future, to regional and local authorities to decide when they alert local populations against or about these hazards. And that's really crucial to work very closely with them so they can effectively get out the messages and it's not coming from us.
Of course. Generalize for me, please. I mean, when it comes to catastrophic rainfall, obviously we talk about climate change. One of the earliest images that comes into people's heads, apart from melting ice caps, is the arid nature of continents like Africa, the spread of the deserts there, the lack of rainfall, the deforestation, the lack of the grasslands, or disappearance of them. And then obviously there are other areas where precipitation is increasing.
Right.
I mean, are you seeing those more catastrophic precipitations? Is it that the actual aggregate rainfall is going up in places, or is it simply that the ground is becoming more vulnerable to cause catastrophes like mudslides and other events like that? I mean, I don't know. Can you give me a broader picture on how that works?
Well, it's both, right? We know that climate change is happening now and the impacts of it are occurring now. And so, for some extreme events like heat waves that are being exacerbated by climate change, they're both increasing in frequency and intensity around the world. We know that, and the science is pretty definitive on attribution of that as a direct result of climate change. Heavier precipitation, with warmer atmospheres can carry more moisture. And so some areas that results in heavier rains, more extreme rains. We see that with tropical cyclones as well. In the United States, we've had 2 of the most intense and most expensive hurricane seasons on record. And so those lead to other impacts like floods and landslides. But at the same time, in the Western US, we've seen pervasive drought, extreme drought. And so understanding the impacts and going back to climate change, it's almost like a 3-pronged stool, right? So we need to understand the physical principles. We need to have consistent observations, and then we have to be able to put those into a model to replicate what we observe in the past and how we can understand that in the future. And so with a big picture, we know these extremes are happening now. We see them, and now we need to figure out how to represent these 3 different elements to get a better sense of what may happen and how it may become more extreme in the future.
Peter, in terms of how you apply your research, looking at Greenland, I mean, how are you pushing this forward? Is it simply about creating a model to tell us how quickly, and by what proportion this vast mass of frozen water is going to start disappearing into the oceans in the coming years, or is there something more that we can learn about the mitigating strategies or whatever they might be in regard of the Greenland ice cap specifically?
Well, there are many different things you can do, and I tend, in terms of, you mentioned modeling, I tend to not do modeling. I don't. I'm suspicious of it because when I see the predictions of models about climate, they're nearly always wrong when it comes to the polar climate, especially, which has been my speciality, that the the Intergovernmental Panel on Climate Change has a very long track record of under-predicting change, presumably so that they don't frighten the horses. And so therefore, the thing that you really need to do is to go out in the field and do the measurements there.
So you're frightening the horses for them.
Yes. And so much of my work has been done on sea ice, and there we've seen the ice thinning and disappearing, and the result being warming of the coastal waters of the Arctic, for instance. And for that, I've worked a lot actually with colleagues of Dalia. At the there's a very nice snow and ice group at the lab in the lab, and I've worked with them over the years. And there are people there who have a similar viewpoint, that they're collecting data, but at the same time they go out into the field. And I've been out on icebreakers with Joey Camiso and colleagues like that. And because you're always finding something surprising. If you're actually out in the field, you see things going on that modelers don't put into their models, and therefore the models don't predict correctly what's going to be happening. So I'm in favour of going out into the field, and then you can see what's going on.
But you're saying that the melt rate is accelerating faster than current modelling is predicting.
Oh, absolutely, yes, it is. And the acceleration of the melt rate has been very visible over the last few years, because if you go back about 10, 15 years, then the assumption in those days was that most of the sea level rise that's observed was due to the fact that the ocean is warming. And as the ocean warms, the density of the water goes down, and the water level stands higher. So you think about a warming ocean giving rise to a very gentle sea level rise, and it's maybe, we've only had maybe 20 or 30 centimeters of that. But as soon as the rate of warming goes up, you instead of just a warmer ocean each year that is giving a sea level rise, you've got actual melting and breakup of parts of the cryosphere that never used to melt at all. Like Greenland never used to melt. At the surface of the Greenland ice sheet, which is pretty high elevation, about 3,000 meters or so, you used to never get melt, even in summer. Now it's melting like crazy. Similarly, the Antarctic was also never observed to melt. And then it's gradually, the quantity of melt per year has gone up. And now we're seeing unexpected events which could have a big impact in one go, like the destruction of the Thwaites Glacier, for instance. There could be a single event that could cause more than a meter of sea level rise. And in fact, the predictions now for global sea level rise, which by IPCC, which I think are still wrong, are predicting about a meter by the end of this century. But most of the people who work on ice and see the processes going on are saying it's going to be much more than that, maybe 4 meters. And that's
4 meters. 4 meters by the end of the century.
Yes, that's been the opinion of somebody I respect very much, but unfortunately died. And in fact, he died in an accident on the Greenland ice sheet. That was Connie Stephan, very experienced Swiss glaciologist who had a research hut on the ice sheet, and he fell down a crevasse and was killed last year. But his view was that the rate of warming that's being put about by IPCC is hopelessly low, and he's thinking about 4 meters, and other people are thinking about something a lot more than 1 meter. And
And
that
the latest report from the UN, the panel on climate change, which just got released right this week. Am I right? I mean,
yes,
that is still sticking to that forecast? You're still saying it's massively over optimistic.
yes, they haven't. Well, that particular report wasn't specifically about sea level, but there'll be another report about that. But it is, I think, optimistic, and that's very dangerous. For instance, a couple of years ago, I was taken to China by a British delegation to discuss with the Chinese Academy of Sciences sea level rise, and we found that the person in charge of Shanghai's making preparations for Shanghai's sea level rise was working with an old figure that he got from an earlier IPCC report, and he was estimating there might be a 50 centimetre rise in sea level by the end of the century. And he was responsible for the network of sea level canals in Shanghai. I mean, Shanghai has got hundreds of canals crisscrossing it. And because what you really need to do is to build up the banks of those canals so that they can withstand the amount of sea level rise that's going to happen. But he hadn't. He'd followed to the letter the predictions of IPCC. And there's going to be a disaster there at some point, unless they appoint a new person to be in charge of China's sea level rise.
You mentioned Shanghai. There are many cities equally enormous, which are presumably even more threatened. From Mumbai to Miami.
Well, quite close to me, where I am at the moment in Turin, is Venice, and the Venice gates, which are supposed to protect Venice from storm surges, and they've been so many years late in installing them that they're already obsolete, and you're going to have to do something to raise the height of them, because sea level rise is already taking care of the amount of rise that they were designed to cope with.
Dalia, I mean, I'm just going to ask you, what are your thoughts? I mean, how does this chime with what you're seeing?
So I am not a modeler in terms of contributing to IPCC, what have you. One of the things that I'm really working on is trying to design the next set of observations from satellites to understand changes to the water cycle. I mean, we know that things are happening now, but there are a number of different satellites, even airborne instruments in development to help us understand the water cycle and really to close the water budget. And what that means is you have all of these different changes. You have evapotranspiration, so what the water coming from plants, you have precipitation changes, you have changes in actual levels of our lakes and rivers. And so what I've been focusing on is how we can understand the interaction between precipitation and aerosols. So these, aerosols, little tiny particles in the air, water vapor can glom onto them, and they can actually create more intense or more frequent storms. And so we're working at NASA to develop the next generation of high resolution estimates of our surface and the atmosphere, so we can start to understand the individual particles, the microphysics, all the way to the big picture. And that feeds into the models. And so the better observations we have, along with ground references, which is fundamental, then we'll be able to better predict what we see in the future and improve those estimates over time. So I think
the cycle, what you're describing, I mean, maybe it's not this crude, but you get more spreading deserts, places like Australia or East Africa or West Africa, and more dirt in the air, which as it travels in the stratosphere then attracts more particles to create more precipitation. So therefore you get more storms as well as more dry areas. I mean, is that how it works? It's probably not necessary.
Well, the aerosols mostly travel in the troposphere, which is the first 10 kilometers, right? So if you imagine, I mean, there's some pretty amazing visualizations and models, but all the dust, the dust coming off of the Sahara, right? Coming into the Atlantic Ocean. So you see these storms that are starting to form as a result of that dust. And so the interactions those aerosols have, that dust has, it actually controls the energy exchange. So how much energy is being absorbed in our atmosphere, but also it affects storms and how that transports all the way to us in the United States in the form of more extreme storms, right? So we have more water vapor, there's more heat trapped, and there's a warmer ocean layer. All of those ingredients are kind of the source of making stronger storms, and that's what we've been seeing. We also see that these storms the hurricanes are starting to slow down because of the amount of warm water we have in the surface, as well as the types of winds that are prevailing. And so that's some of the stuff that I study. And by being able to kind of connect those processes, we will do a better job at helping to understand in the near term storm severity, right? So where is the cone of concern for some of these major systems? The intensification of those, which is a huge challenge. We just saw that with Hurricane Ida that devastated New Orleans just last year. To try to understand the near-term impacts, but then use that to improve our understanding of the physics of these systems so that we can look into the future.
What are the implications of a slower hurricane?
Well, so one example is from Hurricane Harvey, right? So Hurricane Harvey hit Texas, and because it was over really warm water, it sat for 2 days and caused 40 inches of rain inland in Texas, right? And so that is a tremendous amount of rain. And so by basically the hurricane straddled the coast, right? So it got the warm water from the Gulf, and then it rained out over Texas. And so those types of storms, in addition to storm surge and impacts from sea level rise, we have more severe storm surge. That inland coastal flooding is huge for water quality, for obviously impacting infrastructure and people and populations. And so we are seeing more of that as the storm dynamics are starting to change.
This may not be your field, probably it isn't, but I'm going to raise it because I do politics quite a lot. And I think it's a question that's come up already actually in what people are sending in. But the geopolitics of this is interesting, isn't it? We talked about water wars almost, I don't know, I've been doing it for the BBC for the last 20 years, like all the prospect of it. And there never is quite a water war. There is just always a war that's clearly got a lot of water kind of roped into the background tensions that have led to the conflict. Are you seeing a sense that is playing in more with the regions that you're looking at, that there is more competition going on in populations in this? Well, how is the human population interacting, I guess, in these areas where there's been enormous water scarcity as well as intensity?
Is that to me?
Yeah.
So, I think that the way that I'll answer that question is that in order to understand where there's going to be water security issues in the future and in now, to me, one of the things we've been working on, for example, is understanding the agricultural context for this. So there's a program called the Famine Early Warning System, which operates in Africa and Central America, really all over the world. And so it's bringing in different satellite and ground-based observations with models to understand water scarcity that can lead to food shortages, food insecurity, and ultimately, can trigger famine or some of these conflicts. And so it's a multi-agency effort. It's NASA, US Department of Agriculture, USGS, USAID, Agency for International Development. Together, those types of integrated efforts help us to understand where conflicts might be, or where food shortages might be, and to provide that to populations all over the world to get a better handle on some of those water scarcity issues that could ultimately lead to conflict. But I mean, at NASA, our goal is to provide the information and be objective and highly, integrated, integrate that information into systems that can help people to understand, but we are not the ones that are making policy. We're helping to inform it.
Of course. Peter, are you helping policy, do you think? Or do you think the policymakers ignore you and wish you'd go away?
No, well, no, I don't. I think I'm helping.
With your 4 meter forecasts, there are a lot of people, as you know, in the world of climate advocacy who are terrified when things get too terrifying, because it's very hard to sell a message of hope in that environment.
Yes. Although I think that the more information you have, the better, because for instance, Dalia's been talking about hurricanes, and you need a lot of integrated information to be able to do any sort of prediction there, because, for instance, we've had over the years, we've had a big program in the Greenland Sea, opposite end of the world, in the Greenland Sea, funded by the European Union, to study chimneys, which are a way in which the surface water of the Atlantic Ocean sinks, and it's called the thermohaline circulation. So the water is driven by temperature and salinity variations. It sinks in the Greenland Sea through these mysterious chimneys, which are like great plug holes in the ocean. And what turned out to be the case is that these things disappeared a few years ago because the climate got warmer, and so the chimneys, which are made from the formation of sea ice in the region near the ice age, they're not forming anymore. And when they don't form, then the rate of motion, or the average speed in this circulation, thermohaline circulation, slows down. And the predictions of a model based on that are that with the surface water flowing more slowly, part of that circulation is water flowing from the Gulf northwards into the North Atlantic. That's going to slow down. In fact, it's going to slow down and help to cool Britain, and it will make Britain less hot. But one of those things is that it increases the heat content of the water in the Gulf, and you get more violent hurricanes. So the hurricane violence is a product of something going on at the other end of the world in the Greenland Sea. So you need huge amounts of data, and you need observational models, observations and models that stand across a large number of disciplines in order to really be able to make a prediction about what's going to happen, and then maybe do something about it. Although I'm not quite sure what we can do about the disappearance of the Arctic chimneys.
It is enormously complicated, of course, Dalia. The physics of this is massively complicated. I was looking at a headline before we started. Climate change is intensifying the Earth's water cycle faster than predicted. It sounds like similar to what we've just been hearing from Peter about the acceleration of the ice melt. Are you seeing that this is a kind of a spiral, a kind of a vicious cycle going on in the water cycle globally?
Well, I mean, we know that the impacts on the water cycle will be most noticeable as a result of climate change, right? So we know that theoretically, one of the challenges is we still haven't been able to directly observe all the different parts of the water cycle. And so I think the important thing, just to echo Peter's point, is that we need to look at this as an integrated system, right? So we can't just look at precipitation. We can't just look at the changes in lake levels or reservoir levels. We have to start or continue to expand our awareness of how we can integrate that information. And I think that is very much kind of why I'm hopeful, is that while we don't have all the measurements now, we do have an increasing capabilities to integrate models and observations to get a better handle on the movement of water in the water cycle and watch how it is changing. And so in my area, which is disasters, we start to see this and see the frequency of extreme events be more prevalent in some areas, both in the absence and the presence of water. But I do think that we're launching 4 different missions, NASA is, with partners this year alone, to look at wind speeds and on the surface to understand hurricanes better. We are looking at, with our partners, to look at sea level rise with their evaluate the world's oceans and their role in climate change with SWOT, the Surface Water Ocean Topography Mission. We are NOAA, we're launching 2 of NOAA's satellites, JPSS-2 and GOES which is launching hopefully tomorrow, to really look and improve our understanding of lightning, of precipitation, of clouds, to really understand the dynamics. And then we have, instruments going up to the International Space Station that can look at mineral dust and the impacts on climate change. So while I know that this sounds really scary, and it is, I think that as we do more field work, which is fundamental, and we increase our awareness of observations, sharing them in an open forum. All of NASA's data is free and open, and we're working with partners that are opening up their data as well. I do think we're going to uncover the changes to the water cycle that we can then do a better job to mitigate. So that took your question and kind of took it all the way out there, but I do think it's important to note.
Absolutely, but I mean, you talked about, and we talked about the extreme events in different places in the world. And
Yeah.
Is there anywhere where extreme events are not getting more extreme?
Probably, yeah.
Well,
I'm just wondering. Sorry, yeah. Peter.
No, I was trying to think of a place where, one of the problems with climate change, wherever you look, whatever part or aspect of climate change you look at, is that everything is speeding up. And I think there was a late scientist who said that one of the problems with mankind is inability to understand the exponential function, because that everything is speeding up, and is, when you thought, for instance, with sea level rise, you think when you're on an exponential curve, you're walking along on the flat, nothing much is happening. You're thinking, oh, there's nothing happening into the global sea levels, because here we are just very slightly coming up, and then suddenly you're walking up a cliff. So this is true of global carbon dioxide levels, for instance. Everything we've done over the years hasn't had the slightest impact on carbon dioxide levels. They've continued to rise exponentially. And if they're rising exponentially, then the amount that they are increasing every year is itself increasing. So this is true of whatever you look at, pretty much, in the climate. We are really in a climate emergency, in the sense that every aspect of climate change appears to be accelerating. There's various feedbacks which act in that direction, always seemingly to make things worse. That is, they're called positive feedbacks because they make things worse. So I was trying to think of something where extremes are no longer happening, but I can't. I think the extremes are getting worse.
Dalia, I mean, do you see the physics at work meteorologically as well? I don't know. Maybe you're not a meteorologist, and you tell me that's not what I know. But I mean, are you seeing the same kind of feedbacks that Peter was describing, applying in terms of the physics of rain patterns?
Well,
accelerating them.
Yeah, so I'm not a meteorologist, actually. I'm a geomorphologist, but I think that what we are starting to understand more and more is kind of how water vapor is changing, right? So warmer temperatures in general means you have more space to have water vapor in the atmosphere, and so that can cause more extreme storms. We're seeing that, right? We know that that's happening, and I think that understanding the physics and the interactions with things, as I said before, with aerosols is critical, right? To understand those, that it's not just it warms up, there's more water vapor, and it rains. There's mountains, right? There are oceans. There are things in the way that that make us have different experiences with precipitation in different communities, right? So climate change is a very personal thing. It affects every community differently, and so when we're trying to understand the physics of precipitation, of snow and of rain, we're really trying to understand how it is impacting a community with all of the different aspects that it has. So trying to understand how precipitation coming off a huge atmospheric river, right, coming off of the Pacific affecting the West Coast. Those dynamics, understanding and forecasting those events is critical to looking at where it's going to hit the mountains as it comes to the west, and then how that's going to rain out and cause floods and landslides. So I think that the answer is yes, but there's a lot that's unknown, specifically with snow and mixed phase events, that is still causing us to expand our understanding of physics. And by being able to improve the physics, we are able to improve the models to better predict. And I think that's kind of where the cycle comes around, and we're continuing that quest, but it's making progress.
Peter, do you think you're making a dent on people's awareness with the work you do?
Well, I think
you are today, obviously, but I'm just mean in general,
There's two different ways. One, the main one that is through one's science, but I've also started to write popular books about climate change, which I shall now proceed to advertise. A book called A Farewell to Ice, which I brought out a couple of years ago with Penguin Books. So therefore it's very cheap. And it deals with all the different ways in which ice is disappearing, and sea ice, land ice, and what that's doing to what the feedbacks that's causing to other unrelated parts of the world climate. That there are, where you take away sea ice, you're not just making the world less white. You're changing everything, and the same with land ice. So my view there was we've got to get rid of if we want to save ourselves. Firstly, we have to understand what's going on, and so hopefully this book helped there. But the book I'm writing at the moment is about how to get rid of carbon dioxide from the atmosphere, because I feel we can't actually do anything about the climate, particularly if all we're trying to do is to emit less carbon dioxide. And that's more or less what IPCC says we should do, is emit less carbon dioxide, and then things will get better. But they won't, because you can't actually make the climate cooler that way. All you can do is warm it up more slowly. So we have to actually take carbon dioxide out of the atmosphere if we're going to save ourselves. And the various techniques for doing that are all very expensive, but there's a huge amount of ingenuity going into them just now. So in fact, removing CO2 from the ocean as well as from the atmosphere, so that we can get rid of it in various ways. And so I'm writing a second book about that at the moment. Well,
you'll be glad to know that A Farewell to Ice has already been advertised by Sally on the group chat, so everyone can see it there. I'm going to hand you over to Evan now, who's going to be picking up some of the questions. Evan.
So I'm going to try to synopsize a little bit, because we have a bunch of questions that are following a couple of themes. One theme, which was just recently brought up again, is relating to your satellites, Dalia. So someone's asking if you're using Sentinel. Ursula Benz is asking if you use Sentinel-3 or Sentinel-5P. And then John Wells was asking you to describe the GPMs.
Yes, so we use the whole Sentinel series. In my research, Sentinel-1, 1A and B, and Sentinel-2 have been really useful for high resolution optical data and the synthetic aperture radar, which is having some issues, but hopefully it'll be back online soon. So we absolutely take advantage of ESA's satellites. And then for NASA, so I just want to mention that we collaborate and we partner with agencies around the world to launch these satellites. The Global Precipitation Measurement Mission is one that we co-lead with the Japanese, the Japan Aerospace Exploration Agency. And so that was launched in 2014 to provide the most detailed picture of precipitation around the world. So we use active sensors, setting out active signals to sense rainfall in 3 dimensions, as well as passive sensors to look at everything from light rain to heavy rain and snow. And so together, those instruments, as well as a constellation of other satellites together give us this global view every 30 minutes around the world. And that's been really important for global modeling of the water cycle and things like crops, understanding crop forecasting and agricultural yields, soil moisture, et cetera. And so another important observational record is Landsat. So we just launched Landsat 9 late last year. And that, along with Sentinel, allows us to explore how land use is changing, right? So how our forests are changing. There's actually a combined Landsat Sentinel data set that's, I think, going to be released soon, if not already, to allow us to observe at 30-meter resolution kind of how our forests are changing over time. So those are really powerful data to start to diagnose the water cycle in more detail and project out into the future.
Perfect. Thank you. Sorry, I just accidentally hit my stop video button. So Peter, there's a couple different questions that I think are relevant to you as well here that all follow a similar theme. Mark, who you did the interview with, our CEO, Mark Anderson, asked you to describe a little bit about what you'd been talking about back then, which was, you know, the sudden extreme events, these kind of sea change, I guess I would say, no pun intended there, events that might really throw things. Someone asked about nonlinearity, which was kind of brought up earlier this morning. And someone else asked about exponential growth, changing to nonlinear growth. So I think that's kind of a good theme. Do either of you, and particularly let's start with you, Peter, do you see these sudden changes happening where the previous patterns that modeling was based on are just kind of blown out of the water?
Yes, I mean, one that's particularly worrying at the moment is methane. Or as you say, methane, and that is that there's a whole area of the Arctic Ocean which has actually got sediments which are full of methane. It's a sort of strange. The Arctic Ocean is a very strange place because it's that a large amount of it is shallow water, less than 100 meters deep, and that shallow water has got very thick layers of sediment underneath, which are largely methane combined with water to produce a solid, and that is beginning to break up because it's held in place by a layer of permafrost, and because the ice has disappeared, the water warms up in the summer, and you're getting temperatures. I've measured 11 degrees there in the summer, and you get warm temperatures like that. Then the layer of permafrost that protects the world from that amount of methane goes away, and it's already every year people go there and you can see this going on, and eventually it'll all go away, and there will be a big outbreak of methane from the seabed, and that outbreak, it's been calculated. Well, we'd calculated it, could give you a sudden temperature rise of maybe 1.4 degrees. That's a very, very big, it's not big compared to the amount of warming that's going on in the world, but it's a big thing to happen all at once.
How soon do you think that's possible, Peter?
Sorry?
How soon what timeline are we talking?
Well, we're talking, it depends which Russian scientist you talk to. But the fear is it might be in only a few years' time, maybe, because it's happening so fast. It wasn't until I think 2005, which is not that long ago, that the sea ice retreated from the coastal seas of the Arctic at all, and so before then the temperature was freezing point through the year round, and so this has been very rapid change going on, and each year there's more and more of this methane coming up as gas. So there will be a breakdown point at which it all comes out in one go, or a lot of it comes out in one go. And that's something we need to be prepared for, and we can prepare for it. I mean, there are methods of removing removing methane from the atmosphere that are being developed and need to be actually applied. We need to have a kind of a fire brigade in place, ready if this happens, to be able to deal with the methane, so that it doesn't cause as big a temperature rise as is feared.
How about you, Dalia? Are you seeing anything? I mean, I feel like the flooding lately, a lot of the things that you're working on have started to feel a fair bit nonlinear. But are you seeing anything that are you seeing something now that you think is definitely changing into a nonlinear pattern? And do you think that there's something that we aren't aware of that will be a nonlinear pattern all of a sudden?
I have to be honest, I'm not sure, as we see disaster, the nonlinearity that I see is in disaster costs, right? And in the impacts that disasters have on populations, and the fact that, the billion-dollar disasters in the United States, for example, from weather-related disasters, we had 20 of them, over 20 of them in 2020. Is pretty tremendous, $145 billion of damage from weather-related disasters in 2021. So that is absolutely a nonlinear function in terms of the impacts. And so that's kind of where my perspective is, though, we know that there are so many processes that are starting to kind of go on that curve that Peter described. I'll just stick with what I know.
There's another one you could think of that's brush fires, a non-linear process, and the fact that you're getting fires everywhere now, many places where nobody dreamed there could ever be a fire, like the tundra in Siberia, which is normally you think of as wet, sodden, and very cold. Suddenly you're getting the biggest brush fires in the world happening in Siberia, with no way of putting them out. So these are things that are unprecedented.
Yeah, and that brings me to, I think we probably have time for one more kind of broad theme amongst all these questions, which was, and I think everyone wants to hear about this, particularly at fire, which is solutions, right? So the problems that you're witnessing, like these, in Siberia with the tundra finally now burning increasingly year round. I think I've seen tundra fires at really odd times of year lately in the news cycle. All the soot that's going to come from that, reduce albedo, et cetera. Are there ways that you think that we can fix those things? You talked about methane or methane, Peter, but are there other things that you think are grand opportunities to slow down these feedback loops and at least buy us some time, or is it kind of set in stone at this point?
Well, I think the methane can be taken care of if we spend a lot of money before it happens. That will, I think, save us from the worst of a methane disaster. But sea level rise is, you want to keep coming back to that and thinking, I wish I knew a way that we could stop sea level rising, but I can't think of one. And that's the most worrying thing, because most things with climate change, if you spend enough money, you can deal with it. And that's, for instance, carbon dioxide content. That's if you really want to deal with global warming, you can get rid of carbon dioxide by various technical methods if you're willing to spend enough trillions of dollars to do it, and you can. But you can't do that with sea level rise. At least nobody's thought of a way to do it. And that means coastal regions being flooded, poor farmers in Bangladesh drowning or having to move inland. It's global, because the sea is the same level everywhere, and so everywhere you look, the coastal impacts of sea level rise are going to be occurring.
Dalia, do you have any comments here? Finish up.
Yeah, I mean, I'll say that I'm an eternal optimist, but also a realist. And so I think, as scientists, we have tools to measure how our planet is changing, everything from methane to, changing carbon dioxide to the impacts on agriculture, for example. And then we can project those into the future. So the better we can do at observations and modeling now, the more informed decisions we can make about the future. I do think that, around the world, groups of scientists working with policymakers, I saw a comment about how can we better articulate these challenges, I think that makes a huge difference. And we're seeing that come together as social scientists, community leaders, and scientists and policymakers come together to exchange ideas and ultimately make plans that at a local level that they can deploy for global impact. And so I think that we really need to start locally. I'm optimistic in the sense that some of the most extreme scenarios, and maybe this is an arguable thing, but the most extreme scenarios are becoming less likely because of these low carbon energies that are being deployed, but we need to do far more, of course, to build resilient societies. So it has to be a combination of helping to curb these carbon dioxide and other greenhouse gases at a local level, but also build more resilient societies to cope with and to evolve to address some of these impacts.
Yeah, as a person in the Pacific Northwest, I think the rainfall this year reminded us all that we're not safe from climate change either, and we might need to build in some resiliency. All right, thank you all for your time. I know it's precious. We really appreciate it. It's been a fantastic panel, and I appreciate that we've got multiple people coming from different time zones, which is always tough. So thank you, everyone, and I will see you soon.